All right, good morning, everybody, or good afternoon, depending on where you are. My name is Nick Fastine, and I welcome you to my AFT webinar about solution control, specifically why you shouldn't be touching that if you have any troubleshooting issues that you're trying to figure out within your model. Not touching solution control can be useful in a lot of ways because generally if there's an issue in your model, not finding convergence is more an indication of an issue within the model itself rather than an issue within the solver. And really, rather than not touching it at all, we're going to figure out what the different components of solution control mean and what parts we should feel comfortable tweaking and touching so that we can find a converged solution and continue on with our engineering work. And with that, we'll go ahead and get started. We'll take a look first at our agenda. And so first thing we're going to do is take a look at what is solution control, why these things need to be defined in general, the difference between an analytical solution and an iterative solution, which brings us to the next point of looking at what it means to iteratively solve a problem. So software, one of the many reasons we rely on it is because a lot of these equations can't be solved by hand. It's not as simple as solving a quadratic equation, for example. So we'll look at some definitions. We'll start building our vocabulary so that as we get into more of the software, we have that background. So we'll take a look specifically at tolerance and convergence, probably the most important topics of the webinar. And then we'll also take a look at relaxation and what that means. This will largely be in Fathom, but we'll also take a look at AFT Arrow specific solution control. So looking at some of the implications of compressible flow and how that changes the solution control methodology. Similarly, we'll take a look at some things specific to AFT impulse. So what within a transient solver do we need to account for? That'll consider things like cavitation that we can model during a transient, artificial transients where there's discrepancies between a steady state solution and the initial transient solution. And so we'll go through some of those specific aspects in the software. But before we get too far into it, let's take a look at what is solution control in general. So solution control really creates a framework for the solver engine to find a solution. Similar to how your model might require boundary conditions like a flow rate or a pressure, solution control is creating those boundaries so that we know if a solution can be considered a solution. If we look at the most general Fathom model, let's say you're opening it for the first time, almost always this specify solution control will be set for you. So these default settings for solution control, even before any users start digging around and messing with solution control, all of that is defined for you. So these default settings, which we've determined over years of trial and error and figuring out what works best, should work for the majority of cases. In your day-to-day modeling, you shouldn't have to tinker with solution control. It should really be reserved only for those times where you're failing to reach convergence or you're finding specific issues with your results. So let's take a look at Fathom, and we'll take a look at a brand new model. So a fresh model, haven't even saved it, haven't even named it. We can see that the specify solution control is already defined. If we click on it, it'll bring us to the solution control window where we have different tabs for tolerance, where we have a pressure tolerance and a flow rate tolerance. We'll get into what these tolerances mean for the solution. We'll look at the differences in tolerances as well and kind of illuminate what all of these words mean. Under the general tab, we have relaxation, another topic that we're going to look into. That'll come after tolerance and the iterative method because it's fundamental to it. Generally, relaxation will occur automatically, and we'll take a look at an example where that occurs. We also have the iteration limit. So as an iterative process, it's basically elaborate guess and check. We want to set a number on the amount of guesses and checks that we can do, so that way our computer doesn't run to infinity and eventually we can exit that potentially endless loop. We also have an iteration span for auto detect. This ties back to relaxation, which we can get into a bit later, and matrix method. So the scope of this webinar won't really cover matrix method. If you're messing around with these settings in particular, you must be pretty desperate. In that case, it might be best to send your model into our support team, and we'd be happy to take a look and see if we can find any issues with the model itself. So there are some different matrix methods which may impact some of the things we're talking about today, but we don't want to change these settings. This is something I am confident of. Matrix methods, don't touch that. Another thing to bring attention to is this keep track of iteration history. This can help a lot in troubleshooting to show how the iterations are changing if it's getting caught on a specific junction. We'll take a look at that example as well. There's also special controls. These are also things that we probably shouldn't touch unless we know what we're doing. So for example, we can disable global mass balances, and we can also disable global energy balances. So obviously, if we're modeling a physical system, mass and energy balances have to be true. So if we get rid of these defaults and say we can disregard mass and energy balances, it may help approach convergence and help in the iterative process, but really those results shouldn't be trusted. So that'll lead into talking about when convergence does mean accuracy and when we should be more hesitant to look at results. So that's a basic introduction to solution control. Generally, when you're building a model, you shouldn't have to worry about it until it becomes an issue as you start trying to run models, get output, and continue on with your work. So the default settings are going to work for the majority of cases. So if we follow true to the name of the webinar, solution control, don't touch that. Now we're all solution control experts. We just never have to change the defaults. So thank you for attending. It's a little shorter side, but wait a second. You guys are all still here, aren't you? Oh, you can't just give them the bait. You gotta show them what solution control is made of. So if you are interested in solution control, or if you're working on a specific model that has issues with convergence, now we can start understanding the fundamentals of tolerance and convergence with reaching a converged, accurate solution in mind. So to understand tolerance, let's first try to understand what iterative solving is. So iterative compared to an analytical solution means that the previous guess is used to create the next guess, running it through a solver, and as those guesses get closer and closer to some final solution, then we can call that solution converged. This is different from an analytical solution where you can do the math and find an exact answer. So for example, if you were solving x squared minus 4 is equal to 0, you can do that analytically by factoring, and you can find the analytical roots of 2 and minus 2. Iterative solving will get you close to 2 and minus 2, or maybe one or the other. But if we have a much more complex equation with much higher powers of variables and all these different interacting effects, then iterative solving can become much more necessary. This can be found in Excel, where it'll generally do the calculations for you, and if you use Solver, that can also do iterative solving. So to do iterative solving, I like to think of it as elaborate guess and check. So if we're doing guess and check, first we're going to need an initial guess. So x naught, in our case, just think of it as a very general variable where x is ultimately the solution to our problem that we're throwing at it. So we provide an initial guess. In the case of AFT software, we're actually going to provide those initial guesses for you. So you won't have to guess the pressure at a junction or the flow rate through a pipe. AFT can provide a close enough guess to start this iterative process. We're going to plug that initial guess into our equation, and we're going to use Newton-Raphson iterative solutions to try to find a root to an equation. So we'll plug in our first guess and we'll determine x new. We'll take a look at a graphical example so that it's much more clear what that system is doing. So once we have x new, we can compare those two numbers and see if they are within tolerance. So I've mentioned tolerance a lot. what does it really mean? So tolerance is an allowable amount of variation of a specified quantity. So in this case, we want to make sure that our variable that we want accurate as possible isn't changing a whole lot between iterations. If it's making these huge leaps, that means that the iterative process probably hasn't gone long enough, and there's still a lot of uncertainty within that solution. If we're going through the iterative process naturally, let's say this is our first iteration, unless we're very good at guessing initial x's, then we're probably going to have to do another iteration. So we'll say that our tolerance is not met. Our change between x's is still very large. So we're not within tolerance, and we'll set our new to our next guess. We'll go through the cycle again, where we plug x in to determine x new, check it against tolerance, which it probably doesn't meet on the second guess, and we'll repeat this process. So this is where an infinite loop can occur and why it's important to have a maximum number of iterations. So that way, if this happens 50,000 times, there's probably bigger issues with your model than just the solver itself. Well, let's say we let this solver run. It gets closer and closer to that root to our equation. And now x is changing not nearly as much. It's not changing so much that it's within our tolerance. So we can say, yes, now our x changes are so small that our solution has converged on an answer. So the second big vocabulary word is convergence, or changes in our variable between iterations is less than our tolerance. It's important to recognize that convergence is inherently tied to this tolerance. That convergence alone isn't going to tell you if your solution is accurate to your system. In the same way, if you misdefine your model, that's not going to be accurate to the physical system either. So it may be difficult to imagine this process, but if we visualize it with a graph, it might clear it up a bit more. So again, iterative solving, I just think of it as elaborate guess and check. So we have our initial guess. In this case, we're going to be trying to solve this function where we can't find an analytical solution for this root. This is ultimately the x value that we want to determine because this is our pressure or our flow rate that's going to inform our $1 million design decision. So the first step is we have our function. Now we're going to guess x naught. So again, AFT is going to arbitrarily provide a guess for you. You can improve runtimes by providing your own initial guesses, which we'll get into a little bit later. But for the time being, we try to make it as simple as possible for you to just build a model and run it. So we have our initial guess, x. Now we're going to look at how we can use this x to determine the next x new. So that involves first evaluating function and determining the slope at that point. So we know this equation, but we just can't solve the root of it analytically. But with this value and with the slope, we can find an approximate point where 0 would be. So by simplifying the problem, we can find our x new, and we can check the difference between those x's. We can check if this change in x is within our tolerance, in which case our solution has converged and we're all set. But again, since we're looking at the first iteration, we have a very large x. It may be irresponsible to set a tolerance that large just to get convergence. So in this case, we don't meet tolerance. We're going to use this xi plus 1 as our x new, and now we're going to plug it into the equation and do the same process. So we're going to determine the value. We're going to use the slope, find that new 0, and now we can use this next x. But first, we want to check if our change in x is within tolerance. If this number is within tolerance, well, it's converged, and we'll say that this is our solution. If it's not, then we can go through the process again finding the slope at this point to try and find the 0. So you can see as you repeat this process, we're going to inch closer and closer to the 0 just by using the slope of the function, which we know. So this is the Newton-Raphson method. You may remember it from your calculus classes in high school or in college. And this is where all of that math went so that you could not think about it and have it all run in the background. So always think back to this process as we're going through these iterative solvings, looking at how variables are changing, how that change is related to our tolerance, and when we're within that tolerance, how we've reached convergence. So where does this come into play within AFT software? Why are we all here? Why are we all talking about solution control in the first place? The first point is initial guesses. As I've mentioned a few times, these initial flow and pressure guesses are provided by AFT, but really it's just giving that solver a starting point. What actually occurs in our software is that it'll solve pressure first independently. Once that reaches its own convergence, meeting its own relative tolerance, then it will go and check the flow rates to make sure those converge as well. Transfer results to initial guesses, something that we'll do in an example here in a few minutes. That can help speed up the iterative solver just by providing initial guesses much closer to the final answer. In some cases, this can help approach convergence if it's creating jumps over, but generally I think of it as just speeding up the iterative solver, or if you're making a tweak to a model, you can use initial guesses from the previous model as a good starting point. We can also take a look at tolerance, which again is the big point that we need to come back to, is how do we define tolerance and why is it so important? With pressure and flow being solved independently, well, pressure being solved first, then flow checking those pressures, each of those variables are going to have their own tolerance associated with them. So those both have to be met for us to consider a solution converged and start making design decisions upon those results. So once we're within tolerance, we have that convergence, and we have a solution within tolerance. So again, it's important to stress that convergence does not imply results are correct. It's only implying that it's within tolerance. Generally, with AFT software, our tolerance is small enough that we can imply confidence just from the base settings. But just trying to make your model converge so that you can keep moving forward with your project or your work isn't a good strategy, because all of those results may not be good. So initial guesses, tolerance, convergence, those are the big three concepts that we need to understand with iterative solving before we move to the next piece. So let's actually take a look at the software, and let's look at solution control again with this in mind. So again, we're back to a blank workspace. We can access solution control either from the checklist or under analysis and solution control. So here we have our tolerance. Here we have our default, which we can always reset to the AFT recommended tolerances by clicking this button. We can also look at pressure tolerance and flow rate tolerance. Again, because pressure is solved first, then flow rate. Both of these default to a relative tolerance as opposed to an absolute tolerance. We'll take a look at what that means here in a moment and how those different things can have implications on your results. Under general, again, we have our keep track of iteration history. And let's actually look at another example so that we can look at both iteration history to show how the solver is going through it. And then we'll also take a look at transferring results to initial guesses. So here's a little preview of some other examples that we're going to be looking at, comparing relative and absolute tolerance. Here we're just going to take a look at the copy of the base scenario, and we want to turn on iteration history. So under solution control, general, we want to make sure this keep track of iteration history is checked. We can go ahead and run our model, and we will pause it real quick. So the solution progress, the thing most people are probably concerned with is looking down here to see if their solution is converged or not, and this overall runtime, because time is money. Why is it taking so long? If we look a little deeper, we can see that absolute tolerance is reported and relative tolerance is reported. So we can also see the number of iterations. So that entire process of drawing or evaluating the function, determining its slope, and determining a new guess, that's happening thousands of times per second. And we can see we have many more pressure iterations than we do flow rate, because we have to converge this head before we can even check this flow rate. One way that we can see that even better is under other actions and history. Here we can see the iteration history itself. So we see all of these pressure iterations. We can see that our maximum out of relative tolerance value is slowly getting smaller and smaller, which is what we hope to see. We hope to see smaller and smaller change. And once it reaches a suitable level, then it will check the flow rate. If this doesn't converge, then it'll check pressure again, and the cycle will just keep repeating. So thousands of times per second, this is what computers are good at, something that would have taken much longer with hand calculations or solving it analytically, especially when you have things like branching flow and pump curves to account for. So again, a good reason why software is so useful for flow analysis and engineering in general. Another thing that we can look at in iteration history, and this will help with the troubleshooting portion of some of the tips that we have, is looking at which piece is most out of tolerance. So it's checking all of these different points within the model to make sure that they're all within tolerance, to make sure that they are all reaching a converged solution. In most cases, there's always going to be one junction or one pipe that is the most out of tolerance. Here we can see J11, or a branch, or a T actually, is most out of tolerance. That's pretty common in what we see because it has to account for flow in, flow out, the pressure loss across it. It's just much more complicated than something like an elbow, which we know has mass in, has to have the same amount of mass out and a certain amount of loss across it. So this can help reveal where an iterative solver is getting caught or where the solver is stuck in your model. So if you run into a situation where your model is running and running and running and it's thousands of iterations in, tens of thousands in, using iteration history can definitely help in that case. So here we see J8, that branch is actually, or that T is actually the most out of tolerance as well. Sorry about the printer running. I guess we're running some new prints. I'm gonna mute just for a moment and we'll just relish in iteration history. All right, so we can see that we have thousands of iterations and we still haven't reached a converged solution. Here we can see that relaxation is also coming up as a topic. And we'll take a look at what relaxation means here in a moment. But again, because it's automatic, generally you shouldn't have to worry about it. If we hit continue, we can keep going. Our calculations are complete. We can manually check that our relative tolerance on our head is to the -8, while our allowable tolerance is to the -4. And our flow rate is to the -5, while our tolerance is to the -4. So that is the most basic example of iterations. Generally, it's happening behind the scenes and you won't need to worry about it. Now, if we want to take a look at the initial guess, if we open up a pipe and go to the optional tab, we can see that our initial guess for volumetric flow rate is blank. Now, this isn't necessary to define to run your model, again, because we're able to provide those volumetric flow rate guesses for you. If we cancel out, luckily we already have some output results and I can tell you exactly how much flow is going through pipe 19. So if we take a look, it should be 300 gallons per minute, likely because of this flow control valve setting that flow rate. So if we go to output, we can transfer our results to initial guesses, say yes. Now if we take a look at pipe 19, we see that this is full. So now we're providing the solver an even better initial guess close to the solution so that it doesn't have to work as hard to close that iterative gap. Generally, what we would hope to see is this would improve runtime since we're cutting out all of those iterations. However, if we hit run, we can see that it still takes quite a long time. This is due to the flow rate relaxation. So in this specific case, because flow rate relaxation is necessary, we'll show you a quick preview of what it's like if we automatically account for it. And now when we run with those results as initial guesses, we shaved 90% of our runtime. So especially with a very large model where it takes a lot of time and a lot of effort to get to that first initial solution, this can definitely help those sequential runs after that initial run and reduce that runtime further. And so we'll get into why this flow rate relaxation sped up results so much here in a moment. But that's everything I wanted to cover here. So looking at initial guesses, tolerance, and a converged solution. So where does it come in? We had looked at our initial guesses. We took a look at our different tolerances and making sure pressure is met before looking at flow. And we found our converged solution that we can do all of our analysis with. So when we were looking at tolerance, you might have noticed that there's two different types of tolerance. So again, tolerance is the solver's criteria for convergence. Only when our variables are changing minimally between each iteration can we consider that variable converged. There's two ways that we can check that change in variable, and that's those two different types of tolerance. So we have an absolute tolerance and we have a relative tolerance. Absolute looks only at the absolute difference between these different iterations. So absolute tolerance will actually require a variable or require units because it's looking at that variable specifically. So if we had a flow rate tolerance, you might be able to set it to 1 gallon per minute. Now for a 5,000 gallon per minute system, that might be an okay tolerance. If it's within 1, that's still less than 1% of tolerance. However, if you use a 1 gallon per minute tolerance on a 2 gallon per minute system, then you're going to have much more flexibility in your results and it may not be as useful. Similarly, if you have a system with some 3,000 gallon per minute flows and some 2 gallon per minute flows, it may not be good to use the same absolute tolerance for both. So really it's useful for consistent magnitudes. If instead we look at relative tolerance, which is the default for AFT software, now we're looking at a percentage change across iterations. So now it doesn't matter if it was a 3,000 gallon per minute flow or 2 gallon per minute, as long as it's changing within 0.01%, then we can consider that converged. So this is useful if there's different magnitudes and we can say that it's more robust, but there might be issues at lower flow rates. So if we look at a system where our flow is 0.001 gallons per minute, just trickling out, if we have a 0.001% tolerance on it, now we're forcing that solver to find a very fine number while it's juggling all of these different variables at the same time. So that brings us to the idea of how changing tolerance can impact your results. And especially if you're only trying to reach convergence, it may not be a good idea to try and widen that tolerance. So the type of tolerance itself can cause issues. Looking at absolute tolerance, as I mentioned before, if we have very different flow magnitudes, that can lead to very different results. If it's super consistent, if they're all 3,000 gallons per minute, then that can be useful, but generally you may not know that ahead of time. So that's something else you have to consider with absolute tolerance is you need to know the approximate magnitude of your results even before you begin the design process. So if you know all your flows are going to be 1,000 pounds per hour, then that can be very useful. in determining what a good absolute tolerance is, whereas a relative tolerance is always going to be more robust because it's based on that percentage change. It's all about that ratio. But relative tolerance can also cause issues for very low flow rates. So as I mentioned, if we have a very low flow, then it's a very tight range that that solver has to solve. So let's say pipe 1 fed into pipe 2. It has a 60 pound per hour range here, but only a 0.0001 pound per hour range in this pipe specifically. So that can lead to convergence issues as well. So while increasing tolerance can lead to convergence just by giving the solver more room, making it much easier for it to consider a solution converged, the quality of the solution can be put into question. So again, relying on defaults is generally the best idea because time and time again, it's proven that it is accurate to physical systems. And again, convergence doesn't mean accuracy. So if you're only looking for convergence, that isn't really the right goal you should be striving for. One other thing to note is that solution tolerance is not the same as physical tolerance. So let's say you have a design system where flow rate can range anywhere from 2,900 to 3,000 gallons per minute. You shouldn't set your tolerance to that 100 gallons per minute, really, because we're looking at a mathematical solution. What's the ideal number of gallons per minute flowing through this pipe given these boundary conditions? You want a very fine resolution, much finer than you would get in your physical system. So while it can run anywhere between the two, you want to make sure the system you're designing isn't relying on that physical tolerance and is instead relying on a calculated tolerance. So the solution is not accurate to that tolerance. It won't be within that 100 gallon per minute, but based on your boundary conditions, based on how you're modeling it, it should work out. Now we can talk about relaxation, which I've alluded to a few times. This ties into tolerance in the iterative process. And what relaxation does is it's reducing the severity in change. So this is most easily shown with an example. So again, we have our function. We can go through the Newton-Raphson process to determine our x new. But rather than setting this x new as our next guess, we're going to apply relaxation and slow that change. This may seem non-intuitive, but really this is applied when the solver is kind of caught in an iteration loop. So imagine a different function where we have our initial guess. We can go find the solution, but based on the curve, it'll overshoot the root again and then go closer to our initial guess. And so as it iterates, it's not going to exit this loop. And so that's where relaxation can help. So this was the auto span for iterations. This is checking that if this happens more than 100 times, then you should probably start relaxing the solution, which instead of creating this very large jump, now it'll start to inch closer and closer to the root. So generally, this is applied automatically because it's not something that you would really anticipate with your system, unless, of course, you're doing secondary, tertiary runs of your system, and that relaxation comes up multiple times. So as I mentioned, relaxation is applied automatically and is gradually reduced as well. So it may still do that loop, and as you close this relaxation further and further, it has smaller and smaller changes so that it can close to this root. One important thing to note with relaxation, and one potential pitfall you can look out for, is that applying too much relaxation up front can lead to false convergence. So if your relaxation is below your tolerance, then it doesn't matter what this change in x is. Your relaxation might be so small that it barely changes x. That change is small enough to fit within your tolerance, and you can get a converged solution. And so that would be a false convergence because it's not really finding the root. It's just meeting that tolerance value. So that's something to be aware of if you are trying to manually set relaxation. And that's also why it has to be reduced gradually so that you don't come up to that false convergence too quickly. All right, so now we can take a look at a software example. So we're going to take a look at tolerances. We'll look at relative tolerance differences, how we can change that number, how that might impact results. We'll also take a look at absolute tolerance and see how that might impact results. We'll show where relaxation is specified, and we'll reiterate that transfer results example, why that was helpful in speeding up the solver. And then we'll also take a look at exploring to diagnosing convergence issues. So looking at iteration history, looking at the solution progress window, some things that we kind of went over already, but we'll just reiterate them here. So if we go back to our example model, I've already batch run all of these different models. If you don't know how to batch run, you can create all your scenarios, go to File, Start Batch Run, and then it will run all of your scenarios in sequence rather than selecting, clicking Run, waiting for it to finish, going to the next one, clicking Run, waiting for it to finish. So this can be very useful if you're not already aware of it. Another thing I want to touch on here, which is more usability, is how to compare scenarios very easily. So how do I know that I actually changed the tolerance in each without going to each scenario? If we go to Tools and then Compare Scenarios, I actually want to be in this scenario to make it easier. Tools, Compare Scenario, and I want to look at my current scenario compared to all of its siblings. So here we have the scenario comparison window where we're looking at a grid. The way I have it set up is only showing the differences between models. So it can also take a look at junctions if you change an elevation or if you change the diameter of a pipe, for example. All of those can be revealed with this scenario comparison tool. So here we're only changing tolerance. We want to isolate tolerance as the experimental variable. So we have our default relative tolerance at 0.0001, pretty fine tolerance, good enough for most cases. We have a 0.1 tolerance, and we have a 0.001 tolerance. So there may be some changes between these two, and depending on the size of your flow rate, you can definitely amplify these changes because it is a percent change. So as we saw with 3,000 gallons per minute compared to 2 gallons per minute, 3,000 has a much wider range of solutions that'll lead to convergence. So we're all set. We know that our tolerances are all set. We've changed both pressure and flow rate. And so all the results that I've gathered beforehand should be good to analyze. So here in output, we're going to look at some multi-scenarios. We want to look at all three without bringing them into Excel. So under output control, by clicking here, you can go to multi-scenario, and I want to select my relative tolerances. So we'll deselect everything, and we'll select those three scenarios, color coded as such, and say OK. So the first big change we can see is the difference between 0.0001 and 0.001 isn't nearly as noticeable as the change from 0.1 to 0.0001. So the reason for that is, again, gradual changes in tolerance. We do see some additional change here, but 0.1 gallons per minute could be considered negligibly changing. And so what we'll actually see is in some cases they should match up, pretty identically. So our flow rates are the same, our pressures are the same, reasonably close. This is due to the control valve artificially setting that volumetric flow rate. Otherwise, we might see even more variation. And of course, with a bigger model, you would see interacting variables creating even more worse solutions. So here we can see 0.1, we have a bigger flow rate change in pressure. So by changing tolerance, you can change the results. And with bigger flow rates, it's going to amplify that difference so much so it may impact your engineering design, especially here with pumps where we're looking at 3 pumps in parallel. Generally, you would hope to see the same head rise and therefore the same flow rate through each pump. With our very loose tolerance, we see 2 are carrying this 3rd pump, whereas with tighter tolerances, they're much closer to running at the same operating point. So that's just a simple example that you could do for yourself with a model that you have of just quickly changing the tolerance in some scenarios and looking at the differences. Let's also take a look at absolute tolerance and see if there's anything interesting there. So again, output control, multi-scenario, and we'll take a look at these absolute tolerances. So here we can see they're actually pretty close. That might be because our flows might be relatively low, or for how high of a flow rate we have, 1 gallon per minute or 1 foot of head might be a reasonable tolerance. Again, this requires that you know the flow rate going through your system beforehand. Otherwise, absolute tolerance may not be super predictable or very useful for determining results. So while there are differences, in this case with absolute tolerance, in this specific case, the big changes are relatively negligible to results. Finally, we can take a look at transfer results as we did before. We should still have our initial guesses in here. And when we run it, because we have our automatic flow rate, we cut off the solver from having to do those initial 100 iterations to see if flow relaxation is necessary. And there it can jump right to the chase, solve it in way less iterations and therefore way less time. So if we want to change our relaxation, again, solution control, general, and here you can make it smaller, but again, you want to be aware of false convergence or accidental false convergence by setting this relaxation too low. Generally, I just recommend staying automatic unless it's revealed by the solver already that you should be using relaxation. All right, I think that is everything I wanted to show here. So now let's take a look at some troubleshooting tricks. So we've touched on a few of them, the first being iteration history to see where a specific area is causing the solver trouble. Usually what we see in our support experience is detailed T's will cause some issues because again, it's handling that branching flow. It adds more complexity. Loops, if you're doing a cooling water system, where now it's kind of implying another boundary condition on the system that not only does all this flow come out, it all has to come back in. Parallel pumps, similar to detailed T's and branching flow, that can also confuse the solver. We saw that with the looser tolerance, how we expected similar head and similar flow rates, but just because of changing tolerance, it had some variation. So all 3 of those things may be causing the issue. The easiest way to reveal that is through iteration history, looking at what specific junction or pipe is running into issues. Something you can do is expand the tolerance for an initial solution, transfer those results, and then tighten that tolerance. That might help with convergence by providing a better initial point for the solver. Pretty self-explanatory. Just be sure to tighten that tolerance again so that you're not making design decisions based on something with a loose tolerance. To speed up solving, similar to transferring results, we can fix relaxation, especially if we see that the solver progress window is applying it automatically, regardless of what changes you make each run. So it's not necessarily a bad thing with relaxation. It just means the solver's caught in a loop. If relaxation can help it get out of that loop, then that's why we approach it that way. And by reducing it automatically, we avoid that false convergence. The final point is looking at the solution progress window. This ties back to the difference between absolute tolerance and relative tolerance and some of the different issues they can run into. So if we see that our absolute tolerance is very low while our relative tolerance is still relatively high, so high that it's not creating a converged solution, you may be able to go into solution control, switch over to absolute tolerance, make sure that it's small enough to cover all of your different pipes, and then run the solver and create a converged solution. So this can be helpful if you have low flow, like that 0.01 gallon per minute example, where that relative tolerance is really over encumbering to that specific flow rate number. So this can be useful, especially if you're getting very high in the number of iterations, or if your model is taking a very long time to run. Just look at the magnitude of this absolute tolerance, see a relative tolerance is relatively big compared to that absolute tolerance, and maybe consider switching it. And so I think that's everything for Fathom. We'll take a look at Arrow and Impulse. Hopefully you stick around if you're those users also. You may be able to learn something about compressible flow and transient flow, but I won't hurt my feelings if you're exclusively Fathom and you've got everything you need. So with that, let's take a look at some Arrow specific solution control. So with Arrow, as opposed to Fathom, now we can't rely on volumetric balances. So mass is always conserved, energy is always conserved. Now with Arrow, we have to account for the compressibility of the fluid itself. Not only do we account for it across the whole system, we have to account for it in each and every pipe. So by accounting for these effects within the pipe, it's going to complicate that iterative process. In essence, we have to cut the pipe up into a bunch of segments that we can solve and capture those compressibility changes. So there's two big methods in Arrow. There's the length march, which takes a pipe, splits it into a bunch of segments so that it can capture the compressibility change from 0 to 1, 1 to 2, etc. There's also the Mach march. So as flow goes through a pipe, pressure will decrease, the flow will expand, causing higher velocity, higher pressure loss, and start increasing in velocity. So the Mach march captures that by looking at the change in velocity rather than looking at how the pipe is split based on length alone. Neither of these methods is the default within Arrow. It's actually a combination, but that's how those two things work. One cuts based on length, so on a certain number of meters it'll cut. Mach march cuts on change in velocity. So if you have high Mach marches or high Mach numbers, like if you're concerned about choking, then Mach march is probably the better option. So rather than going into Arrow, we'll just take a look at solution control within the presentation. So here we can see there's a lot of options. There's a lot more options than we saw in Fathom, largely to do with how that pipe is being segmented. So we can take a look at length march. So the default is length march with Mach number limits. That means initially it'll length march its way through the pipe unless it detects a high change in velocity, at which point it will Mach number march through the rest of the pipe. We can see the increment size over here. That's determining how it cuts the pipe up. So this can help improve the quality of results as well by cutting it into more and more sections. You can get more and more resolution on your answer. However, that will increase runtime just because you're creating more intermediate points to report on, even though you may not need it for your analysis. One other interesting thing to see is these lumped methods. Lumped is simplifying the compressible analysis by looking at the pipe as a single unit. So rather than chunking it up at all, it'll solve the pipe as a whole, both as adiabatic or isothermal. Similar to transferring initial results, what you can do is check this box and it will solve the lumped adiabatic method first, which will be a much easier thing for the solver to figure out, then apply that length march after. So if you keep this checked, it'll do a run of lumped adiabatic, then apply it. Another thing you can do is manually run it as lumped adiabatic, transfer those results, and then you should be set for the rest of your iterations. Or transfer results after you check this, run this, and then uncheck it. So there's a lot of ways that you can skin the cat, especially when you know what you're doing within solution control. So we recommend don't touch it, but if you know how to touch it, then it can definitely help with your analysis. So here's increment size, again, how it cuts the pipe up. Now we'll take a look at tolerance. So here we see there's much more tolerance. Originally with Fathom, we had pressure and flow rate. In Fathom, if you're doing heat transfer, there will also be a temperature tolerance. But with Aero, because the compressibility effects of the fluid is fundamentally based on temperature and enthalpy, there's also an enthalpy tolerance and also a concentration tolerance. So this concentration is because Aero can do dynamic mixing. And with that, it's adding another layer on top of your general flow rate, mass rate, tolerance balances. So that's why these additional components need to be specified. Again, you're probably okay with relative tolerance and using the Aero defaults. But I would recommend experimenting with that solution method, especially if you're running into convergence issues. One little check mark that we sneak in here is the exhaustive tolerance. This just means that each junction, regardless if there's a flow split or not, has pressure solved for it. By default, it's checked because you likely want to double check the pressure of each junction, though you can uncheck it and potentially simplify the solver. Again, I probably wouldn't recommend unchecking this as your first pass in solving a convergence issue or trying to troubleshoot. So those are the tolerances, the additional tolerances specific to compressibility. We can also take a look at the general, where we see our old friends relaxation, our matrix method, as well as some iteration stuff. Here we see some new boxes about temperature and pressure limits. This is to help restrict the solver even further. So if you know we have a maximum and minimum temperature, you can specify that to help limit where that solver is going to go. Similarly with pressure, but both of these are optional. Since we're chunking the pipe into pieces, now we have both global iterations, or how many tries we take at the system as a whole, versus local iterations. So local iterations is as it's chunking the pipe up, going sequentially down the pipe. If convergence isn't reached within 500 local iterations, it'll be able to continue moving on and continue solving the system rather than falling apart and leaving you high and dry. So this local iteration control discusses and kind of handles where that local iteration failure is and how Aero adapts to it automatically so that you can hopefully get a converged solution within a reasonable tolerance. So these have more general and more specific definitions I don't really want to get into here. So you can always click the help menu within solution control, and that'll give you perfect definitions of all of these different components. But again, solution control, it shouldn't be the first place that you're trying to troubleshoot. You should always take a look at the model itself and see if there's any issues you can clearly and easily resolve. All right, so that was all of Aero. So hopefully you're still interested, and we can take a look at impulse or look at some transient control things. In this, we will actually take a look in impulse just because there's a few more pieces to be aware of. So here we can see that our steady solution control is all set, but our transient control isn't. Let's actually look at an example so we don't have to section the pipes. So here everything's defined because it's a pre-built model, but if we go to analysis, we have our same steady solution control. Our tolerance is a little bit tighter than Fathom, so that's something to be aware of if you're importing a model from Fathom to Impulse, is to double check this tolerance. That can cause some discrepancy. General, again, the same things, relaxation, iteration limits, looking at iteration history. The real interesting part is transient control. So here we have things like simulation duration, saving output. The parts that I really want to talk about is this transient cavitation, which we should make sure is checked so that if the system is cavitating, we're able to model the growing and shrinking of that vapor pocket, as well as this artificial transient. So artificial transient is when there's a discrepancy between the steady state solver from Fathom and the initial time step of Impulse. So if there's a discrepancy of more than 0.5%, that should show a flag because it can introduce artificial transients to your system, creating things like pressure waves that wouldn't actually exist in your model. You can ignore low flows, again, because this is part of a percentage, so that may cause issues. But this is really what we should be looking at. Solver threading, this is how the solver is passing out those different iteration steps to the multiple cores of your computer. Again, likely don't need to change this. Artificial transient, you should leave checked unless you're running into artificial transients, then you should troubleshoot the system. And the same thing with transient cavitation. There's also some output things which change your output, but kind of go outside the scope of iterative solving, as well as junction output. And finally, we can see some advanced options, which is a little bit more complex than Fathom's mass and energy balance. So here, these are generally things that you don't want to be touching unless you talk to a support engineer or you really know your stuff about relaxation and tolerance and solution control in general, which hopefully you guys are all experts by the end of this webinar. And so that's really everything I wanted to touch on here. Steady solution control, pretty consistent with Fathom. There is some additional complexity with artificial transients and transient cavitation. And so that brings us to some pitfalls that we want to avoid. A lot of these things you can do, but you really shouldn't be doing. Easiest example is setting relaxation to near zero or trying to set it to zero at all. If we set relaxation equal to zero, iterative solving is essentially pointless. So if we take a look at our previous diagram, let's say R is now 0. So it doesn't matter what our next guess was. Our X new is going to be the same as our initial guess, and it'll just keep iterating on the same number. But the change in X is going to be 0 because our relaxation is 0. So you'll probably get an immediate convergence. Similarly, if you set relaxation very near to 0, you can see that same false convergence. And setting it equal to 0 is actually not allowed within our software. It'll just say, that's not a good idea, you shouldn't do it. So there are some checks on when you shouldn't be touching solution control in the wrong way. Another thing is disregarding that mass and energy balance. So using those special condition tabs in solution control, that can be useful if you want an initial solution to try and figure out where the solver might be running into problems. But most definitely do not have that disregarded if you're making engineering decisions on your model. Some transient specific things, again, looking at cavitation, disregarding it may not make your model run well or may not indicate a severe problem in your system. Disregarding artificial transients isn't a good idea either because that can introduce things into your system that wouldn't exist in reality. In summary, basically, don't change settings without understanding the consequences. You might think to yourself, Nick, that's a really good way of summing it up. I didn't come up with it myself. Came from Albert Einstein, living legend. It's amazing he's still alive today and even thinking about solution control at all. So if you listen to Albert Einstein, you should be okay. Don't change settings without understanding the consequences. In summary, a converged solution indicates the change between iterations is within tolerance. So that could be relative tolerance, that could be absolute tolerance. In no way does convergence alone imply solution accuracy. So if we make our absolute tolerance 10 million, we can get a converged solution really easily, but we should not be making design decisions on that solution. Looking at the results themselves, or if you have a good idea of what's going to happen in the system, whether that's low flow rates or very wide ranges of flow rates, then you can look at the different types of tolerances and how that can improve convergence in a good way by giving you more reliable results rather than the solver chasing a point that it can reach but is arbitrarily too tight. So as we mentioned, absolute tolerance is better at handling those low flow rates because a percentage of a small number is an even smaller number. Relative tolerance is better at handling that wide range of flow rate magnitudes. And so finally, experimenting with solution control can be helpful during troubleshooting. But again, you have to know what you're doing. You have to understand the consequences, know that convergence does not mean accuracy. And in most cases, you should just rely on the default. So while it may be cool to show off all the things you learned and change your tolerance and say, this is why I'm doing it, if you can't solve it with the defaults, then there may be something inherently wrong with the model itself rather than with the solver that's causing it issues. And so hopefully with this, now you feel confident in what solution control does, why a model might not converge, and how to change those tolerances and how to tweak settings ever so slightly to reach convergence while still maintaining accuracy. So hopefully this has been pretty comprehensive, but of course, if you have any other questions or if you have a model that's causing you issues, you can email me or our support team and we'd be more than happy to help. If you have any ideas for future webinars, especially with the turn of the new year, we're looking for some new topics. Feel free to submit a topic to webinars@aft.com. Thanks everyone for attending. I hope this was a good use of your hour and best of luck in your modeling convergence needs. Thanks again.